All right, so let's consider this hypothetical reaction. The rate law is such. An experiment carried out where the starting concentrations were these. The reaction is started, and after 5 seconds, the concentration of A is this right here. We will calculate the value of K for this reaction, then calculate the half-life, calculate the concentration of A after 12 seconds, and calculate the concentration of C after 12 seconds. Okay, so the first thing you need to do is you need to get K. Actually, K actually is needed to do everything else. Okay, and so we're going to start with, well, our deal right here. That's what we'll start with. So we have this rate equals this, and the rate also equals that, okay? And because they both are definitions of that rate, they equal each other as well, right? Okay, fantastic. Okay, so there's actually a few ways you could go around this, but the concentration of the B initial at the beginning of this, notice that is way bigger than A, right? So we've way, way overpowered A. See that? Okay. And so that B concentration is going to essentially not change. Again, does that make sense? Do you see why that is? So remember, in a reaction, if we can only use 10 to this negative second, 0.01 of the A, that means that's the maximum amount of B we could use, right? And that would just round right off. That's smaller than the 0.0 here. See? So you just round that right back up to 6, even if you took the maximum amount out, right? Is that making sense? Okay. So the change in B is just not significant at all. Okay. All right, so essentially during this reaction, the rate is going to end up being equal to essentially K, because B isn't going to change at all, okay? It will cancel out. So we can have K times A, and that's essentially going to end up being that rate, okay? Notice, by the way, though, I'm kind of, okay, so let me step back from that, okay? I need to explain a few things. Okay, so this constant actually has a number of factors in it, okay? And so if this is also a constant, we can take this and just fold it into this K. And then if we have a modified constant, we would normally call that K prime, okay? And if you did that again, where you modified your K prime, it would be K double prime. K triple prime, you get the idea, right? Yeah. So what that means every time we do it, K prime, K double prime, is we're folding things in, we're folding constants into it, okay? Remember though, they have to be constants, okay? We're doing that because they won't change. Okay, and so you can represent that rate. That was rate equals K times the concentration of A times the concentration of B squared. Well, B isn't going to change, so that's a constant. That B squared is also a constant, right? And that means that can be folded into K prime, okay? And so we can simplify our equation to make it, well, the rate equals K prime times A, the only thing that changes, okay? And that'll make our lives easier, so we don't have to solve so much stuff. Okay, so the next part we're going to do then is, well, what is K prime then? Well, K prime is then K times B squared, isn't it? And so then we can solve for K later, once we figure out the K prime. I'm just setting that up now, okay? Because it's just easier to do there. All right. Why did I do that? Well, we have two states, don't we? Yeah. We have the state where we time 0, right? What we began with. Then the second thing we have is we have the A concentration after 5 seconds, in my case. See that? Okay. And so we have 2 states. Remember that K is constant, right? The K prime will be constant. It won't change. There we go. Okay. So we can take one equation and divide it by the other one. So we have the one at time 0, which has the concentration of the natural log of the concentration of A at time 0 this time, in this case, right? Because that one is 4 times 0. That's going to be divided by, well, this one right here, A, right? Okay. And that's going to equal negative K prime times T. Does everybody see what I'm using? It's the integrated rate law. Look at your rate laws again on that sheet. Okay. By the way, how do I know the order for this? How do I know the order for A? So what are the orders? Well, in the rate law, if you have the rate law, then the order is just the powers up here, isn't it? So for example, in this case right here, the order with respect to A is first order. The order with respect to B would be second order. Yeah. And the total order for this reaction would be what? Tertiary, supposedly, right? Third order. But again, that doesn't actually mean a lot. It's useful to know, but yeah. Okay. So I got my first order one that's been solved for me, right? So I don't have to do a lot of extra work. And if you look back in my lecture, I do a little solving of that and show you how that gets solved for. That's actually one rate law over the other, isn't it? Okay, so I have my at whatever time, right? Over time 0. That's going to equal the negative K prime times T. And so I put my values in for my natural log, so natural log of the time, that number I got for that time, right? Divided by what we started with. That's going to be equal to negative K prime times 5 seconds, right? I go ahead and do this in my calculator. I divide it by 5. And I'm going to get K prime equals this number here. Okay. Did I lose anybody? No. Right. Please do not feel fearful of saying, yeah, you lost me, because that's how you can benefit and get something out of this. Oh, yeah, 5 seconds, the time. Yeah, so if we just put it in here, it's K prime times 5. But yeah, we'll have to divide it over to get our answer, which is K. We'll get our K prime value. And don't forget to flip the sign, because it's negative K prime. Okay, did everybody get down to here okay? Yeah, please do let me know if you get lost in there, because it's fair. I mean, a lot of people don't practice this stuff for a long time. All right, so for the reaction, though, we don't want K prime. What do we want? K, right? No prime. And so K prime, well, that equaled K, which we're going to try to figure out, times B squared. So we can just take some value for B, right? Okay. And so we take our K prime, We divide over the value of b squared. So there's our k prime. We're dividing it by the 6, because it doesn't change, at least not significantly, squared, right? Which would be 36, by the way. All right, and then that would give us this value right here. Okay. Our units, if you're ever trying to figure out the units, the easy way to do this is to go back up to your rate law, okay? So remember, your K has to cancel out most of the units for your rate law. And you have to be left with some form of molarity over time, right? So that concentration over time, okay? And so here we would have, well, that is molarity, right? This would be molarity squared. That means total, this would be molarity cubed here, right? That means you need to get rid of 2 of those, don't you? And then have a time in the bottom. So your units for this would essentially be molarity to the -2, seconds to the -1. Or another way of representing that would be liters squared, because liters would be on top now, if molarity is on bottom. Moles -2, seconds -1. Okay? Which it actually tells you right there. So I just wanted to go through how you figure that out, okay? Because sometimes people do ask you questions, and I want to cover it. Okay. Did everybody get that okay? Fantastic. 2 sig figs, because multiplications, and there's a bunch of 2 sig figs, right? So. Okay, fantastic. Right. Once you have your K, then you can do your half-life actually very easily, right? So all we have to do to get the half-life is just take the formula. Okay? And so using the, we'll use the equation for the half-life for a first-order reaction, because we're going to look at A. We can use the K prime to make it pseudo-first order. That's, again, why we did that. It makes our life so much easier, okay? Okay, so if we're first order, that's the time 1/2, half-life, equals natural log of 2, which is just, natural log 2, divided by will be our K prime, because we want it to be pseudo-first order, okay? Is everybody understanding why I'm saying pseudo-first order? We got rid of the term for the constant, B, which would have made the entire thing third order, right? Yeah. And we're only left with A, which is first order. That's the trick we're playing to simplify everything. Okay. And it should come out like 3.6 seconds. Let me know if anybody gets lost or doesn't understand anything on there. While people are working on that, I'm going to mention that when you set problems up, grid problem solving would dictate that you go, what do I have, what do I need, and how do I get there, right? That's just good problem solving for everything in life, okay? And one of the things you can do while you're stating what do I have, what do I need, and how do I get there, is look at your numbers, okay? If you have huge differences in concentrations, you can actually start doing things like simplifying your math, simplifying your conditions, because those huge differences are going to mean that you will not have significant changes in one of the numbers, right? So you're going to see that later in equilibrium, and I'll actually point that out later in equilibrium in a really big way that will make a very long problem very short. Okay? Okay, then the next part is we're going to do the concentrations. Let's go ahead and have you folks try those first and see if you can get those by yourselves. without me doing anything. Okay? I'll ask you a quick question. D is super easy to do. So if our maximum number we can reduce these numbers by is 0.01, if you changed 2.0 by 0.01, so 1.99, what would that round up when it's 2 sig figs? 2.0 again, right? See that? So again, we don't change that significantly, do we? Okay. So D, it's just the same number, 2.0, because it doesn't change significantly. All right. Okay. Let me try to indicate in some way that you're done whenever you're done, okay? That way I can know when people are worked out. I'll give you a little hint. We did a prompt just like this a little while ago. I'm going to go ahead and scroll on down, and we're going to talk about it, okay? Okay, so remember the pseudo first order rate law that we did before? We can just use the same equation. We now have K, right? We have a time, we have initial concentration, so we can just solve for the concentration at that time, okay? And so we take that same equation, again, that's our initial concentration right there, right? That's the concentration we're trying to look for. Before we had that concentration, now we don't, right? Because we're trying to do a different time. That's going to be equal to, again, our K prime is going to show up because it's much easier to do this as a pseudo first order, right? We can make our lives much easier. And that's going to be times over here on the right, the 12 seconds, which is the time that this one's for. That makes sense to everybody? Fantastic. So we solve. Does everybody remember how to get rid of the natural log? Yeah. Okay. Very good. So we multiply these, we'll get a number. Or you can just wait until you do the rest of it to actually simplify things. Either way will work. We'll be left with A over the 0.01 over here on the left. We'll have e to the power of whatever that is. And then we just multiply over 0.01, do that in our calculator. I won't even try in my head. And that would give us 0.0981. All right. I think I have this number wrong. That should be like 0.0000981, something like that. Could somebody check that for me? And by the way, if you ever do the math on these, one of the things you should always check out is this concentration has to be some number lower than what you start with, right? Because it's getting used up. So that number's actually higher. That might be the number before I multiply over this 0.01. I think it is.
When I just put the part in there, it comes back as basically the same thing.
Okay.
0.9749.
Yep. So if you put e to the negative power of this stuff right here, it comes out with that. And then you should multiply over this right here.
Multiply that number.
Yeah, because you have to multiply both sides by this number to get rid of it. And that should give you the 0.000981, or 9.8 times 10 to the negative 4. I forgot how I have it in there. All right, and that's that. Did anybody have any problems getting down there? Get lost anywhere? Okay. Any specific area, or you don't know why we started? Okay, so there is the integrated rate law that you would get for a first order reaction, right? We used the same thing up here, and that's the rate law right there. Okay, so it should have been natural log of the concentration of A at the time we're talking, divided by the concentration of A at the beginning, initial, times 0. That equals? Oh, yeah, we have the time 0. The time 0 will never change, yeah. Yeah, you'll put in time 0. We have that, it won't change. Yeah, so what you should end up with is the natural log. We're looking for that natural A concentration at that 12 seconds, right? And it's divided by the A times 0, which was listed up here. That value right there. And then that will be equal to the K prime, the negative K prime. And this is one place people oftentimes get confused. We need the K prime to be pseudo first order. So you're going to use that K prime value for all these. And then that's times the time, which is 12 seconds. And we got the time right here. Okay. Did that clear that up, or? Okay, are you not understanding why, do you understand why we're using the first order rate law here? The first or integrated first order rate law? Huh? Okay. So go ahead and write down the equation first, okay? So we can be clear. Okay, and that's the natural log of the concentration of A divided by the concentration of A0, which is the initial, equals negative K prime T, which is the time. Okay, and then the K prime is what we determined in part A before we could get our K no prime. Okay, and we want to keep using the K prime for pretty much everything, because it makes it pseudo first order, okay? Okay. The A0 is this number here that we were given at the beginning. We don't know A, so you just leave that bracket A. That's what we're going to try to determine. Okay. And then the k prime has that time next to it. And so the time was given in C. Now, it may be the math steps that are an issue here. So you got that equation set up like that, right? Same numbers as shown here? Okay, fantastic. So what I would do to make your life easier is I would go ahead and multiply these first before I do anything else. So negative 0.194 times 12. Okay. So then you'll have this equals some number here. Okay? Okay, so when you try to get rid of a natural log, you have to take e to the power of both sides. So e to the power of natural log will cancel, just leaving you with a over 0.01 on the left. On the right side, you'll have e to that negative number that you got just a little while ago. So when you take e to that negative number you got a little while ago, what do you get? Do you not get that? Okay. Can you make some time during my office hours or come by after this and I can look over your shoulder, okay? That'd be fantastic. Yeah. Does everybody understand why D just ends up with the same number? Yeah. Okay. So D is actually only going to be, so the maximum amount of C that can get used is going to be 2 times that value right there, right? Because it's 2 of them were used for every one of these. And so if you take 2.0 minus 0.02, you would just round it right back up to 2.0, wouldn't you? Okay. And so, yeah. It doesn't change significantly. Okay. And we are